So we know that real hardware depends on the availability of resources in the overall Kubernetes cluster. We know that there are CPU and memory limits, and it's actually kind of really simple, right? I've described that we can make a mistake here, but in that mistake, then settings for the heap size exceeded the limit of memory for a pod. Wasn't that harmful? So the service still worked for some time until it was overloaded and ate all the memory. So JVM tries to survive in that circumstances, and Kubernetes also waits for it, well, to actually break the rules. So if there are no load, if you prepared your system for a normal work, and that normal work has its own pattern, and you can still have a work in production, right? And if you're lazy enough, things just work, but sometimes things happen. And that's what happened with one of our friends' case. They do have Black Fridays, and they have to survive Black Fridays and to serve their clients. So they need a lot of resources again. So these are days of especially large spendings for their business, for their FinOps. So we have to scale. Well, as I mentioned, there are different types of instances still. Some of them may be very hardly involved in that Black Fridays or whatever, well, hard activity. So they need dedicated resources. They need a clear, strict quality of service. Then they are never in a situation then their resources are not enough. Other services can be co-located, can be kind of packed, stripped of resources because they are less critical, they are not overloaded. So that's where you can save a lot. And all different systems that try to tune or figure out some recommendations for your Kubernetes cluster, they say, okay, you can use spot instances and save like 40% of your spendings. All right, but that doesn't work for that heavy lifting ones. So for them, you have to be careful, right? And this is the focus of this talk. Because for not so overloaded services, it's very simple. There are many ways to save, and sometimes they survive incorrect settings. It's less critical. So, and less critical, and in the end, it's less costly. And when we talk about that overloaded services, we need to watch that SLAs, right? And it should be consistent when they scale. So sometimes people do pre-scaling, for example, just to keep instances ready for action before they're actually used. So here we know that we trade some underutilization for performance, but this is a wise trade, right? We just need to understand how we pre-scale, what strategy do we select here, like how many instances do we keep in advance, or how do we increase the number of instances, the number of pods. So another thing here is that even if we scale, for example, a service that uses a database, we might not get the result by just increasing the number of instances. Why? Because it has its own dependencies, and we have to scale them first. Like if it's a database that is able to process only like 300 requests per second, right, on one instance, and we have multiple instances of a service all go into a single node of that database. they won't give you more than 3,000 or 300 requests per second for all of them, right? Because they all depend on the single instance of that database. So you have to scale that database or other dependency first. On the reverse, if you scale that too much, it's underutilized. So you should shrink it and keep your front layer untouched, right? Because you can save resources by reducing the number of instances that are dependencies for your front line. And we know that services break. So we have sometimes not a pleasant situation when our pods are being shut down, or we have bad performance, which is in many cases equal to the situation here. Like if an instance still runs but doesn't respond, well, it's effectively dead, and that situation must be monitored, and this instance should be restarted, or you have to have some compliance or investigation of what happens. So let's look at some examples. A very series of very naive experiments with an application that you probably know very well. So this is just a pet clinic example, but we'll assemble some containers from that application. In two ways. We'll build a classical fed jar and also a native image out of it. And surprisingly, see here that jar is only 40 megabytes and the native image is like 124 megabytes. But that tells you nothing. That's just a microservice, which is over 100 of megabytes. But it contains all good parts, like in-memory database, some monitoring, etc., some resources. So how do we pack that into a container? By the way, who uses build packs here? No one, really? Who heard about build packs? Well, great. All right. So who uses handwritten Docker file? Yeah, probably the majority still. That's fine. It's not wrong. I would do that. I would do that myself. While there are some pros and cons in different approaches. All right. Other well-known tools are like Jeep, for example, or some people just don't use containers. They create operating system packages. Well, it happens. Well, maybe that's a scary step. So we had our application, it worked, especially if it's an isolated thing that just does some processing. And now they're going to orchestrate or to transfer it in the cloud. And there are some kind of magical tools that are still not that magical because they won't put memory settings for you. So, for example, for Azure, like cloud providers like to bring users' workloads to their clouds, right? And it means that you previously could have a workload working on a bare metal on some operating system. So tools like that can analyze your environment and produce a container that tries to match all that you had before. So you could move your application to the cloud. And what they also do, such tools, they try to catch all the settings necessary to plug into that cloud. So they generate boilerplate. So you could deploy to a managed Kubernetes, for example, in Azure. So you see, I won't be happy to write all that stuff by hand. I never want to see it. So tools like that help to generate that boilerplate. And as I said, you don't have proper memory options for your Kubernetes, for your containers. Some of your options that you've used previously in your bare metal environment or your virtual machine instances, they can be copied blindly. But there is no guarantee that that settings will work well. Especially, we know nothing about real container requirements and limits. All right, plain old Docker file. Can we do it? Yes. Here's the old Java version, by the way, but that's just for this example. Who knows the recent version of JDK 17? It's 1707. Yeah, and here there are multiple options of what you can have in your from clause. Except please never ever nowadays write OpenJDK there. Because if you go to Docker Hub, you will see that this is a deprecated image. And some images there, like you get it, and they are 1 year old, like dozens of vulnerabilities, like use some secure alternatives. We can tune different stuff like proper non-root user or effective usage of temp directory. We should expose some ports here. And a tiny detail in this exact Docker file is that we can use entry point instead of CMD, because this Alpine image contains shell that allows you to have exec that replaces the main process in your container with this Java. Anyway, just for the reference, ask me what does it mean after the talk. I mentioned build packs, and that's a cool thing to automate stuff, because, well, if we build container ourselves, there's a lot of work. We have to care about the base image precisely. We have to calculate all that memory options, right? The important thing that I omitted on this slide. So here we have run percentage of 80%, and it means that we hope all the native stuff won't occupy more than 20% of our container memory. And we don't have limits here, but we expect them to be big enough, right? Expect them to be sufficient. And build packs create a build pack for you, and it contains some small script used as a starter for your application. And they assemble the resulting container, and you can use either a command line or maybe a Gradle plugin to do that if you use Spring Boot, for example. And different build packs sometimes are replaceable, so you can tune your pipeline when you build a container or anything else. So that's a generic approach to building stuff. So everything you need is either, well, a pack, right? A build pack and some IDs, or plugins, and again, they do all the things for you. Another thing for containers that you need is running container management system, like Docker. So there are some settings, particularly in Spring Boot, that allow you to switch between classical JVMs and native images, right? This is very simple. You just change one property. And then you build such a container, you either use Liberica JDK inside, or you will use Liberica native image kit to compile a native image like the one that I have mentioned a few slides ago. So this is just a standard command that you can use. You, again, need nothing. You need your project, like derived from a template from Spring Boot starter, and command line and run in Docker. And two stacks will be used for your build pack. One stack is used to build the container, and another stack is used inside the container to run your application, right? And the second one is more lightweight. You don't need all the development tools. Like in case of native image, you don't need to compile any more native images, right? If you already have one running in your container. And then we start such a container. I'm not sure if it's visible quite clear, but things happen. This starter script tries to determine the actual resources available. And it has some smart settings, like how many threads do we use for Tomcat? That many. And it calculates tries to calculate some native resources that we will use for sure. Some guaranteed amount of memory will be eaten by your native needs. And all the rest is being passed as a Java heap, right? This is very convenient. There's also some option about reserved memory, like you can plan of how much you will spend for GC. Again, after applying native memory tracking analysis. So we have this started. And by the way, that script is written in Go, and some tooling around that containers and build packs are written in Ruby, and it all runs on either Linux and it uses Java. So it's a nice combination of technologies. But in the end, you get it very simple. It's all under the hood. So basically, we always have control over all of JVM options for our running Java, right? But it's not always so good to set them explicitly. Instead, we can just give hints to the starter scripts for build packs that will tweak final options looking at that settings and on actual resources that we have. All right, so we can build images in different ways, like the ones that I use here. For example, we can use a handwritten Docker file. We'll have the minimalistic Docker image under 100 megabytes. Or we can use build packs. So we'll have like 229 megabytes. Now it's slightly over it, actually over 300. Anyway. Or we can build a native image, again using build packs. You see the container is smaller, but this is not always true, because if your application is big, the native image can become big as well. So it's complicated. How do we optimize our application for containers? But what about sizing our containers? That's what cloud ops try to do, or platform people try to do. But my point is that it should be done in development and early testing. And we'll see how. We'll just take that application, package in different ways, take real hardware and try to put some load, a very trivial load on one of endpoints in that application. And we'll analyze response times, latencies, and we'll analyze throughput, the number of requests per second that we process using that load. So this is a bare metal instance. A part of it, the major part of it is devoted to the application, and small part is devoted to this harness. And we also should keep in mind what actual instances are possible in our deployment, right? If we deploy to AWS in EC2, there are only certain instances available for managed Kubernetes, right? So we have few options to test. And if they provide some amount of memory, it doesn't make sense to use less than that, right? Because you already pay for that. What's the point of making it less? But we'll start with the application itself, no containers. We'll just limit the amount of CPU resource by using simpler tools, and we'll limit heap. And we'll see what's the performance of this application. So it's probably not written on slides, but all the latencies after warm-up must be under 100 milliseconds for 99.99%. And we see that native images in this setup give better result, much better result. So the maximum throughput that we can get within the limitation of our response time, worst response time, is like 1,100 requests per second. A native image gives us more, like 2,400. And I'm not that good in tuning Tomcat or Spring Boot. I can't get it better by JVM options within that limitations. As I mentioned, we have a warm-up. This is not really like it's written, like it's drawn here. It's just this application warms up very well in 60 seconds. So we have stable response times or stable request per second. But in the very beginning, we have Java code being interpreted, so it's slow. And our latencies are very bad if we measure there. So if we measure all the application lifetime, we'll have very, very bad performance. And the latencies are always distributed, so we have some responses that are quick and some responses that are slower. And we probably have few of such slower responses, but they are also important. So we can run that application in a container using just not Kubernetes, but Docker, just a single container with a single application. And we already see some decrease here. So it costs like few tens of requests per second. But if we put that application to Kubernetes within a single node, ingress, service, and a single pod, what happens? The performance drops dramatically. Only 600 requests per second, and it doesn't cost by the ingress. So for this application, there's a high cost in putting that into a container and then putting that container to Kubernetes. And if we skip this experiment, nobody would know that we can get much better performance until we reach production, or nobody know that at all. So yeah, you see, Kubernetes is bad. Right? So let's try to add some pods there. What will happen? How do you think? So we now have a working cluster, we have an ingress, and we increase the number of pods. Well, we have better performance. So by using 4 pods, we restored the initial kind of close to initial performance, right? Using the same machine, same resources. We just split it differently. What's also interesting here is we should analyze the CPU consumption. And typically, CPU consumption is higher on startup for classical JVM because JIT compilers work and then consume resources. And then this consumption drops basically to just 3% if you don't put any load on that, right? So startup time may be unacceptable sometimes if we put too low CPU resources, but it's a waste if we on a long run and we just don't use that CPU. So let's increase it even more, right? Like here, 16 instances, but smaller heap and smaller amount of CPUs, only 2 CPUs, and it's now better, right? So it's super easy, we just change the YAML file, change JVM options as well, and we get better performance, right? But we have to test it. We put some real load. We can make it even worse. Like, let's take only half of CPU and 64 instances. That stuff. I said, don't put less than 1 CPU for your Java applications, right? Well, but we do it here. And no gain, right? It's just, or some gain. All right, what will happen? And these numbers, anyway, they are larger than our original performance, better than our original performance that we have with a single, not containerized bare metal instance. Hooray! Kubernetes is good. What happens with native images? How do you think? Can it be better? Because this number is close to the one that we had with a native image in the very beginning on the bare metal. Well, we can use the same experiment, just a different container. And if we put that amount of instances, we have much better performance, even like 5,000 requests per second. Hooray, Kubernetes is good again. So both native images and classical JVMs, they scale, but you have to deal with some peculiarities, of course. So you have to find your scaling strategy, right? It's how do you try your performance in production, like A/B testing or canary deployments, and what are your actual requirements? What are your limits? You have to determine that, and you have to tune your application settings. You should track your native memory. You should know about JVM internals, like what's the amount of waste for a metaspace or your direct buffers or whatever. And then you build your images, and as I mentioned, deploying that images, it also requires some resources. Then you go to Kubernetes. Like the pod daemon, well, it's like 128 megabytes of your memory resources, for example, not so much CPU. You can do it manually, or you can use build packs to calculate the final settings. These are still important. My point is that JVM settings you should keep an eye on them. You should track what are settings for your running JVMs, and you must select good options, obviously. We know that there are certain things in JVM that helps your containers. For example, if we have slow startup and we are limited on CPU resource, we can trade startup time, have better startup time, and trade it for the size of the container. We can create class data sharing archive, for example, put it in a container image. It will increase the image size, but we'll have much better startup time. We can use alternative ways to minimize that container images by using slim jerrys, like ones that we provide. And of course, we must think about security, like using Alpaqueta Linux in this example. As I said, no sense to place less than one CPU requirements, and we saw that in action, right? So let's apply different tools for containers wisely. When we need to transform our legacy application, we can use cloud vendors tools to do that, to build some container templates. When we automate our CI, please think about using build packs or other similar stuff, not writing your Docker files by hand. And we always must test before we deploy, before we go to production. We should prepare our performance testing along with our functional testing, of course, and there must be a strategy of going to actual prod. Then we went to production. We must still care about our applications. We must collect metrics, and at this point, we are strictly tied to that SLOs that we are committed to. So please ask me any questions. We covered our performance testing mandatory part for Kubernetes today. Yeah, thanks for listening. If you don't have questions, I will show you console. I'm not kidding. All right, so anyone wants to see some build packs in action? Yeah, okay, we have a question. Oh. Okay, request for console. All right, so if we need to build a build pack, this is that simple, and most of the command line is not necessary. That's for guys like me who have different Java distributions on their machines. So here we just invoke Maven and say Spring Boot build image. And it builds an image, right? So you see that's the output. And we have the image in our local container registry after that. We did nothing. We had an application previously, and that's it. If we change it a bit, like we recently added our own build pack with Alpaqueta. This is an alternative build pack. Yeah, that's an extra. We have a timeout, so this is a special, very secret demonstration. And using that build pack, they'll use the very same command to build an image. And we'll have resultant images here. So you can see that yeah, that's for running images. In runtime, after startup, just by using a different build pack, we get a different memory consumption. Like it was like 350 megabytes, and with an optimized build pack, it's like 220 megabytes. So we can use different distributions here. And if you look at image sizes, you see that it again can be very different. Like default build pack is not that bad, much better than kind of OpenJDK images that are 400 megabytes. This one is 300 with the application. And it can be optimized even more. So now if you're excited with memory savings, find me. Yeah. Thanks again.